you for the kind introduction. I'm very happy to be here. And today I'll be talking about our work on the optimality of optimistic responsiveness. Before I start, I want to make sure that you guys can see my screen. Vanessa, can you show? Yeah, okay, sounds great. All right, so today I'm going to talk about our work on optimality of optimistic responsiveness. This is joint work with Nibesh, Itai, and Ling. So today we'll ask or answer two questions. One, what is the limits to latency of an optimistically responsive synchronous protocol? And two, once we understand what these limits are, we'll actually show results that actually achieve this optimal latency. So let me start from the basics. We are thinking of consensus in a state machine replication setting where there are a bunch of clients and there are a bunch of server replicas. These clients are sending commands to these server replicas. The goal of the server replicas is to agree on a sequence of these commands and execute them in a state machine. The requirement that we have is that this group of servers should provide you with the same interface as that of a single non-faulty server. And this should hold even if some of the servers are faulty. For example, the server to the bottom right over here is faulty. It can be a crash fault or it can behave arbitrarily. Yet for all non-faulty servers, together they should provide the clients with the same interface as that of a single non-faulty server. To be more specific, we require two guarantees to hold. The first guarantee is a safety guarantee which says nothing bad should happen. Essentially, it says any two non-faulty servers agree on the same sequence of values or same sequence of commands. And the second property that we want is liveness. And liveness says something good should happen. Essentially, a value or a command that is proposed by a client should eventually be executed by every non-faulty server. So in this talk today, we'll be talking about the latency to achieve such consensus. So once these clients have submitted their commands, how much time does it take for the servers to agree on a block or a sequence of blocks? And whenever we're thinking about latency, one aspect that matters is what is the underlying communication model in between these two any two server replicas. And in the past, people have considered different communication models. People have, at the highest level, people have considered a synchronous communication model as well as a partially synchronous communication model or an asynchronous communication model. At the highest level, a synchrony assumption says that if I send you a message at time t, or if a replica sends a message at time t to another replica, then the message should arrive by time t plus delta, where delta is a pessimistic bounded delay. So you can think of delta as being 10 seconds in a regular network, where if I send you a message, we are guaranteed that it will arrive within the next 10 seconds. Partial synchrony or asynchrony, I'm not going to get into the distinction between these two, but at the highest level, say that if I send you a message, the message will arrive eventually. So given these models, there are multiple protocols that people have come up with. For example, in the synchronous model, one of our own protocols was sync hot stuff that we came up with recently. A more well-known protocol in the synchronous model is Nakamoto consensus, or the protocol underlying Bitcoin. Under partial synchrony or asynchrony, there are protocols such as PBFT and hot stuff that exist. So here is a short comparison between these two models. First, in terms of the assumption itself, synchrony assumption is far stronger because we are expecting that all messages arrive within a bounded delay. With partial synchrony or asynchrony, we do not make that assumption. However, the advantage with a synchronous protocol is that you can tolerate a higher number of faults. We can tolerate 49% faults with a synchrony assumption, whereas with partial synchrony or asynchrony, there are lower bounds to show you cannot exceed a third. However, yet another disadvantage with the synchronous protocol is that typically the latency of a synchronous protocol depends on the pessimistic network delay delta, capital delta, where let's say our pessimistic network delay is 10 seconds, and actually the messages are arriving within a few milliseconds. And by virtue of being a synchronous protocol, your latency typically depends on capital delta, that is 10 seconds, even if messages arrive in a few milliseconds. However, for partially synchronous or asynchronous protocols, the latencies typically depend only on, not typically, they always depend only on small delta. That is the actual network delay. So there are some advantages, some disadvantages. In terms of the assumption itself, one of our prior works, Synchronous, actually simplified this assumption, not simplified, it made this assumption less strong by not requiring all messages to respect synchrony. In terms of latency, our prior work also, one of our prior works actually reduced the latency, but it still depended on delta. Today, we'll try to push that envelope further and try to ask if under good conditions, if we can get better than capital delta. And we'll do this under what is called optimistic responsiveness. So it is known that if you consider all possible executions for a protocol that tolerate more than and over 3 faults, there will exist at least one execution where our latency has to depend on delta, on capital delta for a synchronous protocol. Intuitively, this is true because for a synchronous protocol, if this is not true, then we are actually not making use of the synchrony assumption. However, if this holds only for maybe some executions, and there may exist executions where we can actually commit much faster, and in fact commit at a time better than capital delta, or at the latency of the network delay. And a question then we can ask is, under such optimistic situations, can we commit responsively? Indeed, this was a question that was asked a few years earlier by Pass and Shi, and they presented a protocol which can make use of such optimistic situations. The protocol was called Thunderella, which could tolerate half corruption, a minority corruption. And the protocol said, if some optimistic conditions hold, then we can commit responsively on a fast path. Over here, optimistic means that you have an honest leader and you have less than 1/4 corruption or less than 25% corrupt replicas. However, if these optimistic conditions do not hold, then they will commit non-responsively on a slow path. And these commits will be slow, but you do not need the optimistic conditions to hold. In fact, what they presented is what I will put as a slow path, fast path paradigm, where all replicas start on a slow path and keep committing slowly. If the replicas believe that some good conditions hold, they will switch to a fast path where they will start committing responsively. And if the optimistic conditions stop holding at some point, they will move to the slow path through an intermediate transition phase. In this world, when replicas are in slow path, all of them are in slow path. And when they move to the fast path, all of them together move to the fast path. So they all agree on the path before committing using that rule. Then a key question that comes into picture is, how do I decide when to move to the fast path? So I want to move to the fast path only when optimistic conditions are met. However, there's no easy way for me to figure out when these optimistic conditions are met. So if I try to be extremely cautious and only be very late in moving to the fast path, then I'll have missed opportunities when optimistic conditions were indeed met earlier. So I could have committed something faster earlier, and I'm not going to utilize that. On the flip side, if I'm not cautious and if I hastily move to the fast path, it may be the case that optimistic conditions are not met, and then I cannot commit in the fast path either, and then I have to move to the slow path very soon. And the fact that if I have a slow path or a slow transition phase only worsens the situation. So in this work, we ask, can we actually get rid of this notion of fast path, slow path, and can we try to always obtain optimal latency for such protocols? Well, before answering whether we can obtain optimal latency, first we need to understand what does it even mean to achieve optimal latency in this situation, or what is the optimal latency achievable for any optimistically responsive synchronous protocol. So once we discuss what these limits are, then we will move on to actually achieving this optimal latency. So let me start off first with discussing the limits to the latencies. So we're trying to make a statement to the following effect. We're trying to claim that there does not exist a protocol with certain conditions holding, such that we have these two commit rules having specific latencies. So having two commit rules is something characteristic of an optimistically responsive protocol, because one commit rule holds when the optimistic conditions are met, and the other one holds when the optimistic conditions are not met. In this case, we call it a synchronous commit. So what kind of protocol are we interested in? We formalize this by talking about a Byzantine broadcast protocol with an honest sender. So just to recall, Byzantine broadcast says in this formulation, you have you have a sender, a designated sender, who's sending a value to all of the parties. The goal is for all parties to agree on the value sent by the designated sender. If the sender is honest, we want to agree on the sender's value. However, if the sender is Byzantine or dishonest, then we still need to agree, but we can agree on an arbitrary value. And we show our lower bound for a Byzantine broadcast protocol with an honest sender. And the motivation for doing that is because when we eventually come up with our upper bounds and think of a state machine replication setting, the setting that we want to consider is one where your leader in the state machine replication protocol is honest. So a second constraint that we place on this lower bound is that you should be tolerating at least 1/3 Byzantine faults, because if you do not do that, then I can always use a partially synchronous protocol and asynchronous protocol and achieve responsiveness all the time. So when we think of optimistic responsiveness, we are thinking of only protocols that tolerate more than n/3 Byzantine faults. So these are the two conditions that we have for our optimistic commit and synchronous commit. So in our optimistic commit, we think of a protocol that is responsive, such that its latency only depends on small delta, where small delta is the actual network delay. And this should hold in the presence of some faults. So just for concreteness, let's think of the situation where n equals 2f plus 1, or we are tolerating 49% faults. Then optimistic commit says you should be tolerating at least one fault. This cannot exist in conjunction with the synchronous commit, which has a latency of 2 delta minus order delta when you're tolerating a minority corruption. And we claim that this should hold even when all messages between all non-faulty parties arrive instantaneously. So in that sense, I'm giving you the best possible network that can exist. And even into that network, we are saying that these two latency rules cannot coexist at the same time. In fact, although I have written this as responsiveness with order small delta, it turns out that this generally applies for any alpha between 0 and capital delta. So if you're committing in the optimistic case with some latency less than alpha while still tolerating some fault, then you cannot commit with a latency better than 2 delta minus alpha when you're tolerating F faults. In other words, the sum of latencies of both commit rules should be less than 2 delta. Let us try to digest this statement a little more. And to be concrete, let us think of the situation where n equals 2f plus 1. Here is what the lower bound is essentially saying. Suppose you come up with the protocol pi and tell me that I have an optimistically responsive synchronous protocol. I'm going to ask you two questions. And these two questions will be asked assuming that all messages between all non-faulty parties arrive instantaneously. And you have an honest leader as well. So the first question is, how does your protocol behave when there is only one fault? And you come back and tell me that your latency is alpha. And then I ask you, how does your protocol behave when there are F faults and everything else is good? And you come back and tell me that your latency is gamma. I check if alpha plus gamma is less than 2 delta. And if it is, then I can show you that your protocol does not achieve the agreement property or the safety property. So it does not even give you consensus. And in our lower bound, we actually formalize this by showing a world where if you have optimistic latency less than alpha and a world where you have a synchronous latency less than gamma, then I can come up with a third world where agreement does not hold. So in the interest of time, I'll not go into the details of actually providing a blueprint of the lower bound, but we can discuss that in more detail after the talk if you want. So with that, we have established that our limits to latency is the following. If our optimistic rule tolerates greater than n minus 2f faults, then the sum of latencies of both commit rules should be at least 2 delta. And now I'm going to present a result which actually achieves this optimal latency. Specifically, we show a Byzantine Broadcast protocol that tolerates a minority corruption, and under an honest sender, it shows the following. So in terms of the optimistic commit, we are responsive, and we are responsive assuming more than 75% of the replicas are honest. So you can tolerate up to 24% corruption. Otherwise, in the synchronous case, we commit with a latency of 2 capital delta plus some dependency on small deltas, the actual network delay. So why is this protocol optimal? First, the sum of latencies between both of the commit rules is 2 delta. So if you ignore the small delta terms, then this is optimal given the lower bound result that I just presented. Second, we require only 3 and over 4 replicas to be honest for an optimistic commit. And due to a lower bound, due to one of the earlier papers, it turns out that you need as many honest replicas in such a situation. And third, in terms of the latency for an optimistic commit, we incur only 2 small delta latency. And due to a lower bound by Dolev, Reischuk, and Strong, this latency is optimal as well. So let me give you a blueprint of what this protocol looks like. And because I said this protocol is simple, let me try to convince you what the protocol does within one slide. And I'm going to present just the steady state portion, or the portion when your leader is honest during this talk. So the protocol says the following. You have a leader or a sender who is proposing a value B. He sends it to all of the other replicas. Each of these replicas will simply, as soon as they receive a value, they will just echo this proposal and vote for it. They'll just vote for the first valid value that they hear. So by the way, in this entire protocol, we assume that all of these messages are digitally signed. And if some replica hears more than 3 and over 4 votes for a value, they commit to that value if nothing bad happens. Okay, if a sufficient number of people are voting for this value, then I can commit to it. So what is something bad that can happen? One such event is where they detect a leader equivocation, where the leader has sent a different value B prime as well. So if some events like these do not happen, then I'm happy to commit this. Otherwise, if I do not receive 3 and over 4 votes, then I just wait for 2 delta time after my vote. And again, within this 2 delta time, if nothing bad happens, I can again commit this block, even if I do not have 3 and over 4 votes. So that's the basic protocol in the steady state. So one important thing to note is, given what we discussed with the slow path, fast path paradigm, the replicas are not agreeing on what path to commit to ahead of time. So we are not in this paradigm anymore. At any point in time, replicas keep both of these commit rules open. If the responsive commit rule hits, I'll commit using the responsive rule. If a synchronous commit rule hits, I will commit using a synchronous rule. So we have this notion of simultaneity, which allows us to get a better latency. So let me quickly discuss why these commit rules are okay. So let us first think about the intuition for the safety of just committing a single block. So what is it that we want when we say safety? We do not want 2 honest replicas, R and R prime, to commit on different values B and B prime. Now these commits, because there are two different commit rules, these commits can happen using different possible permutations, different possible combinations. So it can be the case that both R and R prime commit to different values B and B prime responsively. We show that this cannot happen due to a simple quorum intersection argument between these 3 and 4 votes that each of them receive. So these arguments are similar to what partially synchronous protocols typically use. Well, both R and R prime can commit synchronously. Well, we show that this cannot happen due to one of our prior works. This is something that was the focus of one of our prior works. Well, R and R prime can commit using different commit rules. For example, R commits using a responsive commit rule and R prime commits using a synchronous commit rule. Let me provide maybe a bit of information on why this is not possible. Let us say replica R commits a value B responsively at time t. We need to show that R prime cannot commit a different value B prime. Intuitively, this holds for the following reason. Let us think of the situation where R prime is committing B prime before some time t plus delta. If this were to be true, if it is committing using a synchronous rule at some time before t plus delta, because of the 2 delta wait, R prime should have voted for this block before time t minus delta. And this vote should arrive at replica R before time t. And that would have stopped replica R from committing. And for this reason, so again, let me repeat this. So if R prime has to commit B prime before time t plus delta, because of the 2 delta wait after voting, it must be the case that some honest replica must have voted for this block B prime before time t minus delta. And this vote should have arrived at replica R before time t. And this would have stopped replica R from committing responsively because R would have detected a bad event. And for this reason, R prime cannot commit B prime before time t plus delta. Why can it not commit after t plus delta? It's because of a converse argument where one of the votes that R received must be honest. And this vote was made before time t. And this vote will arrive at replica R prime before time t plus delta. And that would stop replica R prime from committing a different value. So this goes as far as we are thinking of the safety of a single block, a single shot consensus. But it turns out because we achieve simultaneity, there are other concerns that we need to tackle when we are thinking of safety, even when leaders change. And one key aspect that comes into picture for us is the following. We can have some replicas commit the same block using a responsive rule or a synchronous rule. But more importantly, all the commits cannot happen, one using responsive and one using synchronous. The underlying certificates or this notion of using multiple votes can happen for conflicting blocks. Specifically, we can have one replica receiving 3 and 4 votes for, or 75% votes for a block, and some other honest replica receiving just a synchronous certificate or fewer votes for a conflicting block. And this actually can create multiple conflicting chains. And at that point, how a replica picks a preferred chain is a challenge that we need to consider in our protocol. So this is something that did not exist with prior protocols because they always agreed on a path of whether we are in the slow path or the fast path ahead of time. In fact, since our protocol was so simple, and it was optimal, we implemented it and we compared it with some state-of-the-art protocols. So on the x-axis, we see different number of faults that these protocols can tolerate. On the y-axis, we see the latencies they achieve in the optimistic cases. That is when you're tolerating fewer than 25% faults. So the 3 curves correspond to sync hot stuff, which is the state-of-the-art synchronous protocol. The second curve, the yellow one, corresponds to hot stuff, which is the state-of-the-art partially synchronous protocol. And the third curve, OptSync, corresponds to our protocol in the optimistic case. And the latencies for these protocols in the optimistic cases are the following. It's 2 delta plus delta, theoretically 6 delta or 6 small delta for hot stuff, and 2 small delta for OptSync. And as you can see, consistently we perform better than all of these protocols. And so again, compared to something like a partially synchronous protocol, hot stuff, we perform better because they require 3 rounds of communication before committing. But in our case, we just require 1 round of communication. I guess I'm almost out of time, but let me just present at the highest level a second result that we have. A second result says the following. So in our lower bound, we said these constraints hold only when we are tolerating n-2f faults, or at least 1 fault. Well, what if we are not tolerating any faults in the optimistic case? In that situation, we show that we can indeed improve our latency, where the sum of latencies of the 2 protocols is actually optimal, and it is delta, capital delta. So with that, I'd like to stop. Thank you. I'd be happy to take questions. So I should mention about this decentralized blog that we have. So this is a blog where we have posts on research as well as some basics of consensus protocols. So we keep posting new ideas that we have, not new ideas, or new results that we have, as well as some posts describing basics. So you should definitely visit it. Also, if you have an interesting paper and you want to post something over here, please let us know. Thank you.
Great. Thank you, Kartik. Thanks a lot. It's time for questions. I can see that Gregory Chopler has a question. So Gregory?
Yes. Hi, Kartik. So that's a nice presentation. Thank you very much. So I presume that that your protocols and the lower bounds apply to authenticated model, right? So authenticated Byzantine. Do you have any insights what happens in a full Byzantine and non-authenticated Byzantine?
You mean when you do not have digital signatures?
Sorry?
So when
if you don't have signatures, yes. Non-authenticated, yes.
So remember, the motivation for why we are doing this is we want to tolerate at the Synchrony a minority corruption, more than 33% faults. And over there, we want to tolerate, over there, we want to achieve optimal latency. And optimistic responsiveness is interesting under that situation. So when you're thinking of a non-authenticated case, when you're tolerating less than 33% of, when you're talking about a non-authenticated case, then there are lower bounds that say you cannot even achieve more than 33% corruption. So in that sense, it is not interesting. So yeah.
I'm not sure which lower bounds you're referring to.
Oh, I'm referring to the Lamport-Shostak piece lower bound, or the
right. And why is it okay? So why is it not interesting?
Oh, because we can always achieve optimistic. So in that world, we can always use a partially synchronous protocol and get latencies independent of delta, right? So we can always achieve responsiveness. We are not concerned about optimistic responsiveness.
Okay, I see. Okay, thanks.